talking about him.
Sorry, Jacob. Sorry about that.
No, it's all good. So anyway, the event was super impressive. Elon only spoke when he showed the Optimus, the new robot. He's building a general purpose robot that will work in the factories. It's very early days, but they showed 2 versions of it. And he said he thinks they could get it down to $20,000. It's going to work in the factory. So it's actually got a purpose. And obviously the factories already have a ton of robots, but this is more of a robot that will benefit from the general or the computer vision and the AI, the narrow AI being pursued by the self-driving team. This is like 2.5 hours of really intense presentations. The most interesting part for me was they're building their own supercomputer and their chips. And the Dojo supercomputer was really impressive at how much they can get through scenarios. So they're building every scenario of every self-driving. I actually have the full self-driving beta on my car. I've been using it. It's pretty impressive, I have to say. If you haven't used it yet, I feel like AI is moving at a pretty advanced clip the past year. If you haven't also seen, Meta announced a text-to-video generator. So this is even more impressive than DALL-E. DALL-E, you put in a couple of words, Friedberg, and you get a painting or whatever. This is put in a couple of words and you get a short video. So they had one of a teddy bear painting a teddy bear. So it looks like you're going to be able to essentially create a whole movie by just talking to a computer. Really impressive. Where do you think we are, Friedberg, in terms of the compounding nature of these narrow AI efforts? You know, obviously we saw poker, chess, Go, DALL-E, GPT-3, self-driving. It feels like this is all compounding at a faster rate. Or am I just imagining that?
Yeah, look, I mean, it's interesting when people saw the first computer playing chess, they said the same thing. I think any time that you see progress with a computer that starts to mimic the predictive capabilities of a human, it's impressive. But I will argue, and I'll say a few words on this. I think this is part of a 60-year cycle that we've been going through. Fundamentally, what humans and human brains do is we can sense our external environment, then we generate knowledge from that sensing, and then our brains build a model that predicts an outcome. And then that predicted outcome is what drives our actions and our behavior. We observe the sun rise every morning, then we observe that it sets, and you see that enough times, and you build a predictive model from that data that's been generated in your brain that I predict that the sun has risen, it will therefore set. It has set, it will therefore rise. And I think that the computing approach is very similar. It's all about sensing or generating data and then creating a predictive model, and then you can drive action. And initially, the first approach was just basic algorithms. And these are deterministic models that are built. It's a piece of code that says, here's an input, here's an output. And that model is really built by a human. And a human designed that algorithmic model and said, this is what the predictive potential of this software is. Then there was this term called data science. So as data generation began to proliferate, meaning there was far more sensors in the world, it was really cheap to create digital data from the physical world, really cheap to transmit it, really cheap to store it, and really cheap to compute with it. Data science became the hot term in Silicon Valley for a while. And these models were not just a basic algorithm written by a human, but it became an algorithm that was a similar deterministic model that had parameters. And the parameters were ultimately resolved by the data that was being generated. And so these models became much more complex and much more predictive, finer granularities, finer range. Then we use this term machine learning. And in the data science era, it was still like, hey, there's a model and you would solve it statically. You would get a bunch of data, you would statically solve for the parameters, and that would be your model and it would run. Machine learning then allowed those parameters to become dynamic. So the model was static, but generally speaking, the parameters that drove the model became dynamic as more data came into the system and they were dynamically updated. And then this era of AI became, and that's the new catchword. And what AI is realizing is that there's so much data that rather than just resolve the parameters of the model, you can actually resolve a model itself. The algorithm can be written by the data. The algorithm can be written by the software. And so with AI,
example.
So poker playing, an adaptive model. So so you're playing poker and the software begins to recognize behavior and it builds a predictive model that says, here's how you're playing. And then over time, it actually changes not just the parameters of the model, but the model itself, the algorithm itself. And so AI, and then it eventually gets to a point where the algorithm is so much more complex that a human would have never written it. And suddenly the AI has built its own intelligence, its own ability to be predictive in a way that a human algorithmic programmer would have never done. And this is all driven by statistics. So none of this is new science per se. There's new techniques that all on their underlying use statistics as their basis. And then there's these techniques that allow us to build these new systems of model development like neural nets and so on. And those statistics build those neural nets, they solve those parameters and so on. But fundamentally, there is a geometric increase in data and a geometric decline in the cost to generate data from sensors, because the cost of sensors is coming down with Moore's law, transmit that data, because the cost of moving data has come down with broadband communications, the cost of storing data, because the cost of DRAM and solid-state hard drives has come down with Moore's law. And now the ability to actually have enough data to do this AI-driven, what people are calling AI, but it really is the same. It's part of a spectrum of things that have been going on for 60 years to actually drive predictions in the world is really being realized in a bunch of areas that we would have historically been really challenged and surprised to see. And so my argument is, at this point,
big data played a big role. Yeah.
Yeah, over the last decade, we've reached this tipping point in terms of data generation, storage, and computation that's allowed these statistical models to resolve dynamically. And as a result, they are far more predictive. And as a result, we see far more human-like behavior in the predictive systems, both those that are, like a robot is the same as one that existed 20 years ago. But the way that it's run is using the software that is driven by this dynamic model. And that's what makes it so incredible.
Allows for a better answer. Chamath.
Okay, I have two things to say, but the first one is a total non sequitur. So you use the term data scientist. Do you know where the term data scientist came from? As classically used in Silicon Valley? It came from Facebook. And it came from my team in a critical moment. This was in 2007. 2008, I was trying to build the growth team. This is the team that became very famous for getting to 1 billion users and, building a lot of these algorithmic insights. And I was trying to recruit a person from Google. And he was like a PhD in some crazy thing like astrophysics or particle physics or something. And we gave him an offer as a data analyst, because this is what I needed at the time. This is what I thought I needed, an analyst, to analyze data. And he said, absolutely not. I'm offended by the job title. And I remember talking to my HR, business process partner, and I asked her, like, I don't understand, what is this? Where is this coming from? And she said, he fashions himself a scientist. And I said, well, then call him a data scientist. So we wrote in the offer for the first time, data scientist. And at the time, people internally were like, this is a dumb title. What does this mean? Anyways, we hired the guy. He was a star. And that title just took off internally.
Chamath, it's funny because parallel, we started Climate Corp in 2006. And the first guy I hired was a buddy of mine who was a 4.0 in applied math from Cal. And then everyone we hired on with him, we called them the math team. And they were all applied math and statistics, PhDs. Yeah. And we called them the math team. And it was really cool to be part of the math team. But then we switched the team name to data scientist. And then it obviously created this much more kind of impressive role, impressive title, central function to the organization that was more than just a math person or data analyst, as I think it may have been classically treated. Because they really were building the algorithms that drove the models that made the product work, right?
Peter Thiel has a very funny observation, not funny, but observation, which is you should always be wary of any science that actually has science in the name. Political science, social science, I guess maybe data scientists, because the real sciences don't need to qualify themselves, physics, chemistry, biology. Anyways, so here's what I wanted to talk about with respect to AI. Two very important observations that I think is useful for people to know. The first one, Nick, if you throw it up here, is just a baselining of, when we have thought about intelligence and compute capability, we've always talked about Moore's law. And Moore's law, essentially this idea that there is a fixed amount of time where the density of transistors inside of a chip would double. And roughly that period for many, many years was around 2 years. And it was largely led by Intel. And we used to equate this to intelligence, meaning the more density there was in a chip, the more things could be learned and understood. And we used to think about that as the progression of how computing intelligence would grow and eventually AI and artificial intelligence would get to mass market. Well, what we are now at is a place where many people have said Moore's law has broken. Why? It's because we cannot cram any more transistors into a fixed amount of area. We are at the boundaries of physics. And so people think, well, does that mean that our ability to compute will essentially come to an end and stop? And the answer is no. And that's what's demonstrated on this next chart, just to make it simple, which is that what you really see is that if you think about, supercomputing power, so the ability to get to an answer, that has actually continued unabated. And if you look at this chart, the reason why this is possible is entirely because we've shifted from CPUs to these things called GPUs. So you may have heard companies like NVIDIA. Why is companies like NVIDIA done so well? It's because they raised their hand and said, we can take on the work. And by taking on the work away from a traditional CPU, you were able to do a lot of what Friedberg said, is get into these very complicated models. So this is just an observation that I think that we are continuing to compound knowledge and intelligence effectively at the same rate as Moore's law. And we will continue to be able to do that because this makes it a problem of power and a problem of money. So as long as you can buy enough GPUs from NVIDIA or build your own, and as long as you can get access to enough power to run those computers, there really isn't many problems you can't solve. And that's what's so fascinating and interesting. And this is what companies like OpenAI are really proving. When they raised $1 billion, what they did was they attacked this problem because they realized that by shifting the problem to GPUs, it left all these amazing opportunities for them to uncover. And that's effectively what they have. The second thing that I'll say very quickly is that it's been really hard for us as a society to build intelligence in a multimodal way like our brain works. So think about how our brain works. Our brain works in a multimodal way. We can process imagery. We can process words and sounds. We can process all of these different modes, text, into one system and then intuit some intelligence from it and make a decision, right? So, we could be watching this YouTube video. There's going to be transcription. There's video, voice, audio, everything all at once. And we are moving to a place very quickly where computers will have that same ability as well. Today, we go to very specific models in kind of balkanized silos to solve different kinds of problems. But those are now quickly merging, again, because of what I just said about GPUs. So I think what's really important about AI for everybody to understand is the marginal cost of intelligence is going to go to zero. And this is where I'm just going to put out another prediction of my own. When that happens, it's going to be incredibly important for humans to differentiate themselves from computers. And I think the best way for humans to differentiate ourselves is to be more human. It's to be less compute intensive. It's to be more empathetic. It's to be more emotional, not less emotional. Because those differentiators are very difficult for brute force compute to solve.
Be careful. The replicants on this call are getting a little nervous here.
Well, they're not processing that. That was an emotional statement.
Do not want to process that one. Well, to your point, during this AI day, they were showing in self-driving, as you're talking about, this balkanization and trying to make decisions across many different decision trees. They're looking at lane changes. They're looking at other cars and pedestrians. They're looking at road conditions like fog and rain. And then they're using all this big data, to your point, Friedberg, to run tons of different simulations. So they're building like this virtual world on Market Street, and then they will throw people, dogs, cars, people having weird behaviors into the simulation.
It's such a wonderful example. Imagine that system hears a horn.
Yeah.
Well, you hear a horn, so clearly there's some auditory expression of risk, right? There's something risky. And now you have to scan your visual field. You have to probabilistically decide what it could be, what the evasive maneuver, if anything, should be. So that's a multimodal set of intelligence that today isn't really available.
Yeah.
But we have to get there if we're going to have real full self-driving. So that's a perfect example, Jason, a real world example of how hard the problem is, but it'll get solved because we can brute force it now with chips and with compute.
I think that's going to be the very interesting thing with the robots as well, is all of these decisions they're making, moving cars through roads, all of a sudden we're going to see that with VTOLs, vertical takeoff and landing, aircraft, and we're going to see it with this general robot. And everybody wanted to ask Elon about general AI, the Terminator kind of stuff. And his position is, I think if we solve enough of these problems, Friedberg, it'll be an emergent behavior or an emergent phenomenon, I guess would be a better word, based on each of these cities crumbling, each of these tasks getting solved by groups of people. You have any thoughts as we wrap up here on the AI discussion about general AI and the timeline for that? Because obviously we're going to solve every vertical AI problem in short order.
I spoke about this a little bit on the Ask AMA on Call-In on Tuesday night. Once Sacks gets it out, you can listen to it. But I really have this strong belief that
the servers crash. There's no AI team at Call-In.
This episode drops.
Oh my god!
Yeah, you guys can try to download the app, but it might crash. So just be careful.
So here's my core thesis on this.
The problem is, Friedberg, that you were 10 times more popular than JCal, so it was unexpected levels of traffic.
Well, you did have an account with 11,000 followers. I mean, it's a little bit.
You're right, JCal. We'll put you on that account next time.
Yeah, please.
Yeah.
I'm starting from zero.
Yeah, that's fair. That's fair.
Yeah, look, my core thesis is I think humans transitioned from being, let's call it, passive in the system on Earth to being laborers. And then we transitioned from being laborers to being creators. And I think our next transition with AI is to transition from being creators to being narrators. And what I mean by that is as we started to do work on Earth and engineer the world around us, we did labor to do that. We literally plowed the fields. We walked distances. We built things. And over time, we built machines that automated a lot of that labor. Everything from a plow to a tractor to a Caterpillar equipment to a microwave that cooks for us. Labor became less dependent on our labor abilities. And then we got to switch our time and spend our time as creators, as knowledge workers. And a vast majority of the developed world now primarily spends their time as knowledge workers creating. And we create stuff on computers, we do stuff on computers, but we're not doing physical labor anymore. As a lot of the knowledge work gets supplanted by AI, or as it's being termed now, but really gets supplanted by software, the role of the human, I think, transitions to being one of a narrator, where instead of having to create the blueprint for a house, you narrate the house you want, and the software creates the blueprint for you.
You dictate.
And instead of creating the movie and spending $100 million producing a movie, you dictate or you narrate the movie you want to see, and you iterate with the computer, and the computer renders the entire film for you, because those films are shown digitally anyway, so you can have a computer render it. Instead of creating a new piece of content, you narrate the content you want to experience. You create your own video game, you create your own movie experience. And I think that there's a whole evolution that happens. And if you look, Steve Pinkner's book, Enlightenment Now, has a great set of statistics on this. But the amount of time that humans are spending on leisure activities per week has climbed extraordinarily over the past couple of decades. We spend more time enjoying ourselves and exploring our creative interests than we ever did in the past in human history, because we were burdened by all the labor and all the creative and knowledge work we had to do. And now things are much more accessible to us. And I think that AI allows us to transition into an era that we never really thought possible or realized, where the limits are really our imagination of what we can do with the world around us. And the software resolves to and the automation resolves to make those things possible. And that's a really exciting kind of vision for the future that I think AI enables.
Star Trek had this, right? People didn't have to work, and they could pursue things in the holodeck or whatever that they felt was rewarding to them. But speaking of jobs, the job reports for August came in. We talked about this. We were trimming 300,000 jobs a month, and we were wondering if the other shoe would drop. Well, boy, did it drop. Over 1 million jobs burned off in August. So without getting into the macro talk, it does feel like what the Fed is doing and companies doing hiring freezes and cuts is finally having an impact. If we start losing 1 million, as we predicted could happen here on the show, people might actually go back to work, and Lyft and Uber are reporting that the driver shortages are over. They no longer have to pay people spiffs and stuff like that to get people to come back to work. So at least here in America, feels like we're turning a corner. Do we want to go?
Cal, can we? Let's talk about the marijuana